Okay, underneath this piece of paper, I have placed a bar magnet. Now I'm going to sprinkle some iron filings around. You can see how the iron filings line up with the magnetic field. So it looks very much like the pattern that we saw in the photograph in the lecture slides. So now you can see what the magnetic field looks like. Okay. But we can't really tell which end's north or south, can we? Well, here I have a magnetic compass. The red end is the north pole of my magnetic compass. So notice as I move my compass, you can see the compass needle lines up with the same pattern that the iron filings do. So the magnetic compass can also tell me what the pattern of the field looks like. But one thing the compass can tell me that the iron filings can't is they can tell me which end is north and which is south. Okay, so the north end of my compass needle is attracted to that end of the magnet, and the south end of my compass needle is attracted to this end of the magnet. So since opposites attract, this must be the north pole of my magnet. And if I pick up the piece of paper, then I can see, yes, here's the north pole, and over here is the south pole. Okay. So both the iron filings and the magnetic compass can tell me what the field pattern looks like, but only the compass can tell me which end is north and which end is south. Okay, now I have my bar magnet mounted in a little cradle that can easily spin. And I want to investigate the law of poles, right? So the red end is the north, so I can see north and north repel, and south and south repel as well. But if I bring north and south together, they stick. North and south stick. So that gives me the law of poles. Opposite poles attract, like poles repel. Okay, now I have a nail with some wire wrapped around it. The wire is red because it has a red enamel coating on it. And so I have a coil with many turns, and then I'm going to connect the ends of this coil to these electrical leads. These electrical leads are then connected to this power supply. It's a DC power supply. When I turn on the power supply, I get a current through the coil, and that should make this an electromagnet. So I turn on my power supply, and now I bring my compass, and I can see my compass needle. My south end is attracted here to this end of the nail, and I move it around, and I can see the compass needle change. So the north pole of my compass needle is attracted to the pointed end of the nail. I move it around over here, it changes. And see, it follows the same pattern as my bar magnet did. Okay. Now what I'm going to do, I'm going to reverse the connections to the power supply. So I reverse the direction of the current. And now look what happens. Now, this is the north pole, since my south pole of my compass attracts the pointed end, and the north pole of my compass now attracted to here. So this is now the south pole, this is the north pole. So by reversing the current, I reverse the direction of the field. So now this is north, this is south, north on the left, south on the right. Reverse the connections. Now I have south on the left and north on the right. So when I reverse the current, I reverse the polarity of the magnetic field. Okay, here I have another coil. This is a big coil, and I've got it connected up to my power supply. My power supply is turned off, but when I turn on the power supply and run a current through here, I create a magnetic field. So I have a magnet here. The red end is the North Pole, the blue end is the South Pole. And I set it here. Now watch what happens when I turn on the power supply. It pulls the magnet right inside. So that's how the solenoid works. When you energize the solenoid, you can attract a piece of iron inside the solenoid because it creates a magnetic field. So I can do the same thing over at this end. Pulls the South Pole in. So I energize it. Here's a compass. So watch my compass needle. See? The dark end is the north end of my compass needle. And so north is attracted here. So this is South Pole. And South Pole on my compass attracts this end. So this is the North Pole. So just like in the other electromagnet. All right, the last thing I want to demonstrate is the principle of an electric motor. Remember we said a current carrying wire in a magnetic field will experience a force on it. So here I have a coil of copper wire. I took the end wires of the coil and wrapped them around here a couple of times to keep the coil together and then stuck out here. So I made this coil by just wrapping the wire around this battery. I have a D-cell battery. The D-cell battery then is going to supply the current through the coil. And then I also need a magnetic field. So I have a magnet here. This is magnet. You can find these. Actually, I found this at a Radio Shack. There aren't any Radio Shack stores around anymore, but I think you can still buy them online. I only paid about $2.50 for this. What's different about this, it's not an ordinary bar magnet where one end is north and one is south. The poles are on the faces. So here I can see this is the north face, and over here this is the south face. But it doesn't matter. I want the poles to be on the faces, and then this will just stick to the battery. So now I have a magnetic field pointing in this direction here, and I'm going to put my coil in there. But in order to get current to the coil, I need the contacts with the ends of the battery. So I just have some bent paper clips. So I'm going to hold one here on that end of the battery, hold one over here on the other end of the battery. Now I've got a little cradle, and I put my coil in here, and there it spins. So I've got a little electric motor. Look at that. So I have current through my coil in a magnetic field, and there's a force on it, or a torque, that makes it want to rotate, makes it want to spin. All right. Now notice the electric motor that we talked about in lecture had a commutator. So we had to reverse the direction of the current every half revolution to keep the thing spinning. Well, I don't have a commutator on this. So to get around that, what I did was these tail wires are what make contact with the paper clips, which makes contact with the battery to get the current. So instead of having a commutator, what I took was on one of these tail wires, I painted it with a Sharpie marker. But I don't paint the whole thing. I need to have contact for half the revolution. So this side is bare, and then when I rotate around, this side has the paint. So when the bare side makes contact, I have connection on both sides. I get a current, and when it flips around to the other side, now this side hits the paint and it cuts the current off. So rather than reversing the current every half revolution, I just turn it off every half revolution. But the coil has enough momentum that it continues to rotate till the bare side picks up the contact with the paper clip again and gives it another push around. And that's what keeps it moving in the same direction. If I didn't paint this side, what it would do, it would just sit there and oscillate back and forth. It wouldn't continue to rotate. So you paint the top half with the Sharpie marker. The bottom half is clean and bare. This side is completely bare. You don't have to do both sides because you just want to cut the current off every half revolution. So that's a very simple electric motor, very easy to make, very cheap to make. You just need some paper clips, some copper wire to make a coil, and a battery, and a magnet. And I'm sure you can find those magnets if you look around somewhere. And it makes a nice little motor. Okay.